So once you've got your equation of motion, we want to find the natural frequencies. Now, if you remember, back when we were looking at chapter 2, we had the notion of natural frequencies and damped natural frequencies. Well, obviously, to find the natural frequencies, we have to neglect damping, okay? And so we take out the c terms in that equation, and we end up with this as our equation of motion, okay? Now, to find the natural frequencies, we have to make a substitution. Okay, what we do is we substitute in a solution for an oscillation, which is given by this, okay? This is one substitution we can make using cosine omega t plus phi, okay? And basically, we substitute we know that obviously the x is the position of the thing, and that's going to have an amplitude and an oscillation of frequency omega, okay? We don't know what omega is, and we don't know what xi is, but you'll come to find out that this amplitude doesn't actually matter. And so what we do is we make the substitution, okay, where I equals 1 or 2, okay, and obviously you take the second derivative of this with respect to time, and you get a minus omega squared come out, and you have the same term over here. And so we'll do that substitution, and if you plug them in, you end up with, you can go through the motions, you plug it in, and you can rearrange it, and you end up with this matrix times by x1 and x2, okay? And you've obviously got over here, you've got a cosine omega t term that if you divide both sides of the equation by that term, it disappears, so we don't need to worry too much about it. And the same could be said for the x1 and x2, but like I said, let's not worry too much about that. This matrix, okay, if I just go back, you can see that what happens here, we end up with x1, x2 times by minus omega squared, okay, and then times by the cosine term. And here we've just got big x1 and big x2 times by the cosine term. Like I said, the cosine term disappears, and this becomes x1 and x2, the double dots disappear. And so you end up with minus omega squared times by m1, okay, plus k1 plus k2, okay, times by x. And here we've got minus omega squared times by m2, okay, minus k2 plus k2 plus k3 times x2, okay, which is where that matrix comes from. And so once you've got this equation, assuming you've practiced it enough, you can often jump straight to the impedance matrix without having to go through the process of the substitution and stuff. If you can recognize that here we've got the minus omega squared times by m1 plus the k terms, okay, minus the k terms that relate to the second mass, x2. And this process, okay, so the stiffness minus omega squared times by the mass, this is known as the eigenvalue problem, okay? And the natural frequencies will be the eigenvalues, the mode shapes will be known as the eigenvectors, and from this equation we can find those things. So to solve the eigenvalue problem, to find the natural frequencies, okay, is what you have to do is you have to take the determinant of that matrix. Okay. Now the determinant of a 2 by 2 matrix, you should know, you take the diagonals, you multiply them together, okay, and then you take these diagonals and you subtract them multiplied together, okay. So it's this times this minus this times this will be the determinant of a 2 by 2. On your formula sheet, at the back of your notes, okay, on the first page, there's a 3 by 3 determinant, and it's a solution for 3 by 3 determinant. I'm not expecting you to remember the 3 by 3 one because it's a bit more complicated, but the determinant of a 2 by 2 you will have to remember. Now, if you take those diagonals, multiply them together, okay, so we've got the first term and the fourth term, that's the diagonals multiplied together, minus the other two multiplied together, you end up with this. If I expand it out, okay, you end up with m1, m2 times omega to the power of 4. Okay, then you've got omega to the power of 2 multiplied by all this lot. Okay, and then omega to the power of 0, you've got this minus this. Okay, I shan't bore you with the maths, but it's quite straightforward to multiply out those terms. Okay, obviously, you know, to start off with, you take k1, you multiply k1 by this, and times this, okay? k2 multiplied by this, and this, and then minus omega m1 squared. m1 omega squared times this times this times this. Okay, and you can see quite clearly that this bit times this bit will give you the first term. Okay. Now, if we replace, for the sake of argument, you don't have to do this, but if we replace, say that lambda equals omega squared, okay, then it's quite clearly this equation becomes a quadratic equation. We've got a lambda squared here, a lambda here, and a lambda to the power of 0 over here. And so there's our quadratic equation. And obviously, if you've got a quadratic equation, you can solve it using the quadratic formula, okay, to find a value for lambda. And it's quite clear that lambda, there'll be two terms, okay, and each of those will relate to natural frequencies, because lambda 1 and lambda 2 will equal omega 1 squared and omega 2 squared. And you can then solve it for natural frequencies to find omega 1 and omega 2, okay. There's two values. It's a 2 degree of freedom system, there'll be two natural frequencies. A 3 degree of freedom system will have 3 natural frequencies, and so on. A 4 degree of freedom system will have 4 natural frequencies, and on, okay? And they'll be denoted by omega 1, omega 2, and so on. And last week when we talked about omega 1 and omega 2 with the Fourier series, they represented fundamental first harmonic, okay? Here they're not related in the same way, okay? Omega 1 and omega 2 are independent of each other, based purely on the dynamics of the system.